We just
Yeah, that's right.
okay. So welcome everybody. Today's speaker is Aditya Desai from Berkeley University, and this talk is about towards exponentially cheap AI.
Thank you.
Please, welcome.
Okay, am I audible over Zoom? Can somebody just confirm?
I
What people there?
yeah, there is.
Okay, just say something.
Hello, hello.
It looks like it's working. Yeah.
Okay,
Everything should be working.
okay, thank you. So thank you so much for inviting me. Today I'm going to talk about one of the pressing issues in AI, which is the cost of AI models. I'm sure that we have been impressed by the level of sophistication that AI has achieved in the past 3 to 4 years, especially since we got to see products like ChatGPT, Bard, and so on, right? But the cost of training and deploying these models is humongous and is consistently increasing. For example, GPT-3, the first version of GPT that was put out, cost OpenAI around $4 million to train. GPT-4 is supposedly costing it $100 million to train. And Gemini Ultra, the biggest model out of Google, has cost Google $1 billion. So why is the cost of AI so high? I'll just move the, sorry for this. Okay, yeah. So why is cost of AI so high? So the reason is that we essentially are trying to build outrageously large models, right? In the past 5 years, we have seen an exponential increase in model size. And this exponential increase in model size leads to exponential increase in demand for resources. So we need more memory, more compute, more bandwidth, and so on. Now, this high cost of AI and high resource usage is at the root of many existing and impending problems. For example, if you think about the societal impact, the AI making technology is not accessible to everyone, only a few large corporations. Not everyone can gain out of the growth opportunities that it has to offer. If you think about the environmental impact, we are seeing huge carbon footprints and water footprints. For example, GPT-3 training needed around 700K liters of water to keep the data center cool at which it was trained. ChatGPT today is estimated to generate around 4.3 metric ton of carbon, which is equivalent to 100 SF Seattle flights. That is just assuming if every user sends just one query per day. And it's not just the environment of society that's going to get impacted. The technology itself is bearing the bad effect of cost of AI. So firstly, the state-of-the-art AI that we have today cannot be satisfactorily deployed on edge devices like mobile phones or laptops, which is the main client-facing devices. But apart from that, the high cost of AI is also causing slow future progress in AI, right? In fact, we are now in the regime where we are seeing diminishing returns in deep learning. That is, if you look at the quality resource trade-off curve, we are at that point where every bit of improvement in quality is going to come at huge investment of cost and resources. So it might be a good idea at this point to ask the question, are we getting enough return on investment when it comes to AI, right? Are we building machine learning models in the right way that can give us the best quality for the given resources? Now, AI efficiency has been a topic of interest for the past, 8 to 9 years. And several key themes have evolved from this. So all the research that you'll see, there are tens of thousands of papers, they generally revolve around these three key ideas. So you see the sparsity, low rank, or quantization. But I would argue that the improvements that you get with these methods are limited. So my question in this talk is, can we go beyond these improvements? Can we get something like a green curve, which can give us much more quality for much less resources? And I'll try to build some solution in a very narrow domain to show you that it's possible, and then go from there. So in order to build AI, which is much more efficient, we need to rethink machine learning. And while doing this, I feel it might be a promising approach to have a probabilistic view. Now, what I'm proposing is I want to merge the areas of probabilistic methods with machine learning in order to get that efficiency that I'm looking for. Why I think this is a good idea? If you look at the probabilistic methods, such as projection, hashing, sketching, they use this cool randomization trick to reduce the resources that are used, but it comes at a cost of some approximation and uncertainty of the result. But we know that exponential improvements are possible if there's a very strong power law in the data. So these algorithms generally process data, right? Now, if you look at machine learning, on the other hand, we know it is robust to approximations. For example, if you think about training, every step is a very noisy update, but still we are able to get to insanely accurate models. Uncertainty often helps regularize the model. In fact, you add layers like dropout to ensure that there's uncertainty in the system to improve the generalization performance. And power law is pervasively found in machine learning, especially in large models. So think about if you pass a single example to a large model, how many number of neurons are going to be active? So machine learning has all those nice properties that make probabilistic methods work. And so I feel like it might be a good playing field for probabilistic methods. Now, I'm not saying that you can just pick these methods and directly apply them out of the box. That may not work, but we need to somehow adapt them to machine learning and then maybe make them work. So most of my work that I have done trying to follow this guideline of merging these two fields is around improving memory efficiency. Now, this has led to some impact in a few particular areas. And while impacting memory, we were also able to improve the bandwidth of compute in some cases. So this is the overview of my published work. And in this talk, I'll mainly focus on trying to improve the parameter memory. That will be the main part of the technical talk. And then I'll give a brief overview of some problems that I'm trying to solve in LLM domain. So let's begin. Okay, for this section, the cost or resources is going to be parameter memory. Okay, I'm going to simplify this cost quality resource trade-off curve. And I'm looking for an improvement which looks like something like a green line. So let's see if that is achievable. So the first thing I want you to note is that the size of memory that you have available, that determines your model size, right? If you have a bigger piece of memory, you can host a big model. But if you have a smaller piece of memory, what do? You essentially build the same architecture with less number of layers, less number of hidden neurons to get a smaller model, right? And that's what you run. The question we want to ask is, can we build better models in smaller piece of memory, right? Now we know that it's impossible to run the exact same big model in a smaller piece of parameter memory, but maybe there's a way to better utilize this computational graph, better utilize the memory to build complex computational graphs. And that is the proposal of elastic parameter memory. So what we're going to do is we are going to disengage this memory from this computational graph and then give you complete control over the memory of this memory footprint of the parameter memory. So that's the elasticity of the memory. So this is something that you can decide. And no matter what the memory is, I'm going to run some complex graph in it. So how do we achieve it? Before going into the details of how we are able to do it, I want to give you some background on what I'll be using. The first piece of background that I need is hash functions. So what are hash functions? Hash functions are these functions that map a given range of integers to another range of integers, right? Now, we want to build efficient systems, so we cannot just pick an arbitrary hash function because not all hash functions are cheap to store or compute. So people have investigated certain subsets of hash functions called as hash families, which are cheap to store, cheap to compute, and have some nice independence properties that I'll get to in a minute. So an example of hash family is universal hash family from Carter-Wigman, 1979, which is h of x equal to ax plus b mod p mod m. So p in this case is a large prime number, a and b are chosen from these ranges. So storing this function just requires a few integers, computing also is cheap. And when I want to choose a hash function, the way I do it is I choose it randomly from this family, right? And the random choice is where the independence properties matter. And why do we care about randomness? We'll get to it in a minute.
So she's already in the base of the.
Yes.
So the hash will help you to quickly access the base or.
Yeah, so we'll get to it in the next couple of slides, what exactly we do. So the second piece of background I need is random predictions. So what are random predictions? Random prediction essentially is a linear transformation. But the idea is if you have a random linear transformation, then you can preserve the structure of a data set under random prediction. So it's a very standard dimensional reduction tool. For example, if you see at those look at those 4 points, right? If you draw a plane and project it onto them, as long as the plane is random, you're able to preserve the interpoint distances to some extent. So we're going to use hash functions to perform random prediction. Now, how does that work? So in random predictions, you have a higher dimensional vector theta that needs to be projected down to a vector psi. So the way to do that is you look at every location I inside theta apply the hash function to the location I, and then you aggregate these elements into this vector Si, right? And if you do that for all the elements I inside theta, all the locations I for theta, then you get what is a projection of vector theta. Now there are various aggregation schemes, but for the simplicity, let's just assume that we were adding things. So we are going to use hash functions to do sparse random projections. The point of doing that is that it's efficient. Now, another piece of thing that we background that I want to tell you is how do I measure whether random projections are doing their job, right? How do I know if random projections are indeed maintaining the structure of the data set? So for that, we need use this simple theoretical setup, which is the dimensional reduction setup. So in this case, we think about an arbitrary vector x, which is projected down to a vector x hat. And we ask the question, how good the norm of x hat approximates the norm of x. And because we're using random projections, this norm of x hat is a random variable. And in most cases, we use unbiased estimators. I mean, the projection is such that the estimate is unbiased. So the smaller the variance, the better is the estimator, right? And we are going to use this to talk about when you want to compare two hash functions or compare two random projections.
So this vector is again the weights. What is this?
So this is a very general setup.
Yeah.
So it's all about comparing how well it's doing.
But how are you going to use it?
So I'm going to use it. I'll tell you. Yeah. So
is that related to the, for example, our IP property, impressive sensing? We try to preserve norms and distances between sparse vectors.
Yeah, it is related to that property. This setup is. No, in this case we're not. So this is X is arbitrary vector. Yeah, so it's related, but it's not the exact same thing as compressed sensing. We don't want to like recover the exact vector X or those kind of things.
So is it a data in space like in machine learning use? What's the paper? Because we want to understand in context of AI, right? So,
yeah, so we'll get to that in the next slide. Next slide will clear out exactly what we are doing.
I have a question.
Yes.
It's not sparse, right? In the LLM case.
The vector X?
Yeah.
Yeah, it's not sparse.
Yeah.
I mean, this is just theoretical setup. X has got nothing to do with anything.
Yeah.
It can be sparse, it cannot be like it may not be sparse. All is fine. We're just looking at the variance like absolute algebraically in terms of X. Okay, so let's get back to the question. How are you going to use the hash function? So essentially, we want to build bigger models in smaller pieces of memory. So let's take an example, which is we have this 2-layer neural network, right? With 4x4 and 2x4 matrices. And now the case is that I only have 6 parameters to be used. Okay, so 3 parameters for each of the layers. So how am I going to construct this dense graph using smaller piece of parameter memory? The idea is very simple. You're going to reuse these parameters inside this matrices. And in order to know where to put which parameters, I'm going to use hash functions. So for example, if you want to know what value to be used at this location 1, 1, I'm going to hash this location 1, 1 inside the real weights. Real because these are going to be realized on the memory. And these weights are virtual because they are not going to ever be going to reproduce completely inside the memory. So this would basically tell me that I should use the value 1.1. And if I do that for all the elements, I use this hash function, then I'm able to populate the entire graph. So I'm able to get a dense graph in a smaller piece of memory. Now, the only question that we need to ask at this point is, can we do a forward pass and a backward pass inside this small piece of memory? Because if we're able to do that, then we can train this model, we can deploy this model in smaller piece of memory. So for the forward pass, the algorithm is quite simple to explain, right? So whenever you access an element of this virtual weight matrix, all you need to do is redirect that access inside this real weights with hash. So instead of accessing v of 1, 1, you access h of 1, w of h of 1, 1.
So in this one, you had 9 weights, right? This matrix are 9 weights.
Yeah, 16.
So now those were different numbers as compared to what you put in them, right? They were different. All 16 were different.
To start with,
yeah.
So to start with, I don't know. I just want to create this model with this computational graph.
So,
yeah, in the standard model with full memory, they were different. Yes.
So you are saying, assuming that you can replace, can you go back to what you're showing?
Yeah.
This one. So it like is all 1.11 will approximate actual value which were there before or what?
So they will not approximate. It's a different way of building models, right? If you compare it with the full standard memory, like full standard model with the full memory, then that definitely has more expressive power, more representation power.
Yeah.
Right. The question is, if I give you 6 weights and I ask you to use a small model, then the model that you will create with only 6 parameters would be ridiculously small. Right?
Yeah, that's
Yeah.
clear.
Yeah, that's the comparison.
One get an intuition, right? So,
Yeah.
so you take the 16 elements.
Yeah.
Is the 3. And you approximate, you replace the real value, what the weights were with these elements, right? Because these are, only 3 elements.
Yeah. So we are not replacing anything.
Yeah.
So that model that you're talking about, it never existed. Right?
But
This-
if you don't use your, that's what I'm going to use, right?
That's true, but only if you have enough memory.
Replaces the architecture.
Yeah,
and
so
then
that's what I-
replace-
Yeah.
Yeah, that's what I'm going to say.
Yeah.
See, if I don't use your chain.
Yeah.
Then I will have 16 values.
Yes.
And now I have 3, which is good with memory, but it will be approximation now. It's not the real thing what I wanted. So
But that's my point.
Yeah.
What do you want? Do you want the architecture or do you want the quality and memory? Like,
just,
yeah.
just say,
Oh, yeah, that is definitely true.
It's
So
not
standard, so
Yeah.
I think the comparison has to be done on the curve,
yeah,
right? It's about what resources you use and what accuracy you get. And there, like, if you're able to spare 2 GPUs, then please build a
Yeah.
big model. But if you only have 1 GPU, what can you do? This is the better way to do it.
So
Yes.
this
Yeah.
is-
Go ahead.
So this is not the same as you quantize them and
No.
proposals and something like that.
No, it's not a post model.
It's not-
There's no model to start with. This is a different model from the beginning.
beginning.
Yeah.
So I think we are confused because we are expecting an example of the hashing stuff, but this is not the example of hashing.
It is a hashing.
It is a hashing, but again, as I said, like you cannot expect the techniques to be directly applied.
In the hashing, you will have to, when you encounter multiple values for the same value, you will have to sum them up, right? But we are not summing them up. yet.
Because this is hashing in the reverse direction, right? So it's not projecting down, it's projecting up, if you look at it that way. And I'll come to that in a second. I'll come to that. And let's talk about that more on that slide as to how hashing is like what is projection and what is happening in this case, right? But let's try to understand what is happening now, right, in the system. The system is I wanted to build a big graph, right, computational graph, but I wanted to use small piece of memory. Now, 2 options I have. One is building smaller model, which in this case would not even give me like a proper single layer because I have 4 inputs, or maybe like it will give me a single layer or something, right? But with what I'm saying, you can basically build any complex graph with any kind of memory, right? Because you can share the parameters across these different weights. Okay, maybe in the next slide, and then we can discuss the same thing. Yes.
I don't understand how we mapping in place.
Yeah. So essentially, like the thing is, every weight here has to be mapped to one of the weights here. So we are using hash functions to hash this location of this weight into this real weight range. So hash functions just map given integers, set of integers to another set of integers.
So the hash function replaces the cost of that matching. Okay? Like,
What kind of cost?
so you would have otherwise needed something showing that all functions were, right? But now the hash function is doing that work for you by sending it from Q1 to back to the location, right?
Can you rephrase the question again?
So you now have these 3 bits from it. So you want to know which were the original Q1 to. So the hash function.
So there is no original. Again, I'm trying to stress this point.
So
That there is no.
You just use just step one that 111 you should replace it by 2.
Yeah.
112 you should replace by -0.4. That's a
Yes. So thing is, your model only has 6 parameters.
Yeah.
That's the original state. And how they are being used is this mapping. That will basically what is happening is the computational graph. Imagine the computational graph of this, right? Computational graph. Now I have these 6 nodes here, and I'm basically like kind of connecting everything. And then that's my new computational graph.
So the hash index is your position. The freedom which you are going to have is probably the parameter in the hash family.
The freedom in what sense?
So the fact that can you go back and show the numbers?
Yes, sorry.
So in this case, the 0, 0, or 1, 1, and the 1, 2 or two on have the same number, right?
Yeah.
Okay, so this one is because they hash the same cell.
Yes.
Okay, so that if your hash function is fixed, they will always, those numbers would be the same. But because you have a freedom to change the parameter in your hash function, that's, you can play with that such that sometimes 0, 0 and 0 and 1, 1 are not going to be the same.
Yeah. So if you change the hash function, this setup changes.
Yeah.
That's for sure. Whether you want to change the hash function is a different question, right? Because once you train this, and if you change the hash function, it will basically just spoil the accuracy of the model.
But you choose.
So you have to choose it before you start the training. Now, the only thing that we do in that, the choice that we make is that we choose a random hash function, randomly choose from the family. And the idea there is that if you have different parts of this model, right? Think about this model. Think about, you have a large model. What parts of this model are important? Now, we have seen that these models can be specified and like quantized and a lot of different things, right? So models have a lot of capacity to get approximated. So in some sense, some parts of these models are going to be very sensitive to accuracy, but there are going to be other parts of the model which are not going to be that sensitive to the accuracy. So choosing a random function, choosing the function randomly ensures with some high probability that two important pieces don't collide. And that is why this would work if it does work, and we'll see it does.
Yeah, I think for simple inflation, to explain this, we have 16 elements. So you 0, 30, and you only have 3. Then instead of putting 0, you just put different places. You
Yeah.
find 2, 1, and 1.
Yeah.
That's all right.
Yeah. So
That's
what?
the way you reduce.
Yes. So that. So what Dr. Shah is saying that, I mean, one option was to just keep this zeros, right?
Yeah.
Only 3 elements, but everything else is zeros. So that would be like kind of sparsifying. So if you think about it in the traditional probabilistic setting, it's either a sparse projection where you zero out things, or it's a hash-based projection where you sketch things. So things are getting mixed together.
That's
And-
better. But
Yeah, and in fact, in one of the papers, we talk exactly about this setup and show that sketching is better than like sparse projections, especially when there's a power law present. So there's some theory around why this is a good idea. Yes.
They are learnable or
No, they're not learnable. They don't have parameters. I mean, at least in this setup, they don't have parameters. You can introduce parameters as long as you're able to write backward function. It's doable.
okay, so we give you time to finish your thing. Keep going.
As long as we have enough time, I don't mind answering questions.
No, please, leave the room at 11.
Okay, then I should rush. Okay, but this is the important part as to understanding like what exactly we are doing. So how do we do the forward pass? It's clear, like you want to access some weight in the weight matrix, virtual weight matrix, you just redirect all the accesses. You can implement that. In case of the backward pass, whenever you generate these gradients for these virtual weights, you basically just aggregate them into the real weight gradients. So you never realize the full model in the forward pass or the backward pass, like full model gradient in the backward pass. Right? So we are able to have a system where we can have independent control on the memory, whatever memory you want to choose, and we can train this model, we can deploy this model. Now, coming back to your question, what is the hashing? Where is the projection, right? So let's look at what is happening in the setup. The thing is that my V is a 16-dimensional vector, right? It's a point in 16-dimensional space. My W is a point in 3-dimensional space. And those are related by this equation, right? V equals R times W. So generally, in projections, we will be looking at the other equation, which is W equals V times R transpose, like reducing V. But in this case, it's the other way around. And by learning W, I'm learning V, right? Now, if you think about what is happening is V is going to lie inside this column subspace that is defined by R, which is defined in turn by my hash function. So in a standard position setting, you would have a point in high dimensional. You will select a random subspace and project it down to that space. But in this case, it is still projection in play, but we are learning the projection itself by restricting the choices for V inside a random subspace. And that is what I meant when I said, like, you maybe cannot directly apply projections to this setting, right? That you do projections, data projections, and then recover and do something else. But in this case, the idea of how do you bring the power of random projections to machine learning? Well, the idea is that you learn the projection. So that is how it relates to the projection. So do you have any follow-up questions on that?
No, thank you.
Okay, so what we discussed in the previous slide, right? It's a good setup. It seems like a good idea to do, but in machine learning, we need to solve a lot of issues. before we can really make it work, right? And there are four sections of issues that I have mentioned here. So I'll talk in detail about the first, and if we have time, I'll go over the others, because everything is kind of interesting. It has some theory and so on, but let's focus on the first one for now. So let's talk about cache efficiency. Setup that I talked about, as it turns out, it is 50 times lower than running a standard model. And the reason is this. So think about recovering three consecutive elements inside the big matrix, right? In a standard setup, with a high probability, you would just need one cache line fetch to fetch these three elements. But in this setup, because they're applying hash functions, and these hash functions are random and have some nice independence properties, with a very high probability, you're going to access three different locations inside this vector site. So you're going to fetch three cache lines and only access one element from that cache line, like each cache line. So that is exactly why the system is 50 times slower for large matrix multiplications. So how do we fix this issue? So the first thing, how do you fix it, right? So you want to access a few consecutive elements. The only thing you can do is you can co-locate them inside this vector site. But when you fetch one element, you basically get the other elements as well. So how do I achieve it? This is how I do it. So let's take an example where weights are used for embedding tables. So in that case, we know that the embedding table is going to be accessed one row at a time. So I'm going to divide this weights into one-dimensional tiles. And I'm going to co-locate all the elements needed inside this tile in vector site. So what I'm going to do is, if you want to access elements inside this tile 2, 2, I'm going to hash 2, 2, the tile ID and not the elements, inside this vector site, and then pull out a chunk of elements to be used in this tile, right? And by doing this, I have essentially got around the problem of cache efficiency, because now if I need this tile, I'm going to pull it out at once in a co-located space. Okay, let's try to apply the same principle for matrix multiplication. So in this case, we know that the matrix multiplication operation is implemented as a tiled operation, right, on GPUs or even on CPUs. So I'm going to divide this into two-dimensional tiles now. And if I want to fetch the elements inside tile 1, 4, I'm going to hash 1, 4. Again, pick out a chunk of elements and then use it for this tile. So essentially, this gives me a general recipe of how to fix the problem of cache efficiency. And the recipe is, you look at a weight, you think about how it's going to be accessed, divide it into tiles of that shape, and then hash the tile IDs instead of hashing the element IDs. So if you do that, let's see what happens with the latency numbers. So in this case, I'm showing you the inference time for matrix multiplications for different size matrices in different columns. And in different rows, we have the memory footprints of the parameter memory. So you can see that if we had a large matrix multiplication, using element-wise hashing is much, much slower. But if you implement the row styling that I talked about in the previous slide, then you can essentially recover most of the cache efficiency.
Aditya, you were using different hash functions, right?
Yes.
So doesn't it affect which buckets you need to get?
It definitely does. It affects the mapping. It affects the computational graph. Everything is affected. So that's a very good segue into my next slide. So now that we have gained this efficiency, the question is what happens with quality, right? Because I have changed the setup, I have changed the hash functions, and I need to get a handle over what is going to happen with quality as well. So how do I compare two hash functions? So I know one traditional way of comparing them, which is dimensional reduction problem, where I just look at the hash functions as projections and think about how the projection quality looks like, right? Let me do that first. So firstly, if you think about the fact in computer sciences, you gain something, you lose something, right? So I was expecting that if I do this hashing, the block-based hashing, which is what is happening in the second setup, the row styling, then I would see some impact on the quality. But if you analyze this in the dimensional reduction setup, where we look at norm of x hat, right, the arbitrary vector x projection, we see that the variance of the block hashing is actually less than the variance of element-wise hashing. So block hashing is not only cache efficient, but it actually is a better projection as well. This is by far the most surprising result that I have seen in my thesis. Right? I was not expecting this, but it's actually very easy to see. So the thing is, the variance actually comes from the fact that collisions can occur, right? And so the potential for more collisions means more variance. But by doing the blocking, what you ensure is no two elements inside this one block are ever going to collide under any hash function. So by adding these correlations, you actually reduce the variance. Now it makes sense. But again, the thing is, like, I don't really care about the setup, right? I mean, it's nice that it shows some nice properties, but I don't care about the setup on the left, which is you have a vector x, you go down to vector x hat, and you talk about norms. But what I care about is the setup on the right, where you have a vector psi, you up project it to vector theta, you have a function on the top of it, you optimize it for some loss, and then you talk about the quality of that model. That's what I care about. Now, the neat thing here is that in linear models, we were able to show that the projection quality, that is quality that you see with this kind of setup, is related to the quality of learning as well. Essentially, in linear models, like the quality of the learned model is essentially the projection of the correlation vectors. We can show that relation. And so if we are able to show that one hash function is superior than other for the first setup, then it also holds true for the next setup. So that means that roast is not only good for cache efficiency, not only a better projection, but also better for learning projections, which is what we are doing here. Okay, so I'm going to, in interest of time, I'm not going to go over the other parts, like even briefly. Yes.
Why didn't you show us the accuracy, the resulting accuracy?
Next slide. Yes. Yeah. So again, a lot of things need to be done in order to make this work, right? But but once we do that, let's try to now compare. Let's see if we are really getting the benefits that we thought we'll get. So in order to compare the existing methods, this is the setup I'm going to use. So I'm going to choose a data set, choose a model, and I'm going to vary the parameter memory sizes, and then see what kind of quality am I getting, right? So in this case, these are some vision data sets with vision models. So on the x-axis, we have compression, which is essentially compression of 100 means that your parameter memory is smaller by a factor of 100 than what would be needed to host the big model, the entire model. And on the y-axis, we have accuracy. Now you can see that the black line, which is the stable RPS, the method that has all the different components and everything is fixed for learning projections, is superior than all of the other methods. And specifically, look at this yellow line, which is what you would get if you build standard models with the limited parameter memory, right? So indeed, standard model building, the way we are building standard models is not utilizing the best out of the parameter memory that you have. And in fact, this yellow line is, you can beat this yellow line with different existing techniques also, right? So most of these techniques are based on pruning. We have some results on lower rank as well. But even if you apply existing techniques, it means that in terms of parameter memory, standard model is not the best way to go, right? There are a lot more alternatives. And among these alternatives, like what we have built seems to be the best. Now, yes.
Aditya, but it is the black line is yours, right?
Yes.
So if you reduce the model too much, yours is the best. But what about the
So, okay. So essentially, you're talking about this maroon line here, right?
Yeah.
That's the only which kind of crosses. So that's added just for the sake of comparison. It's not a fair comparison anyway. This is basically the LTH, the LTR, lottery ticket rewinding method to get pruned models. But that needs you to train the entire model. It's an informed pruning technique, right? Highly informed pruning technique that trains a big model, then prunes it, then prunes it, then prunes it. Like 10 times you do the pruning and then you get this. No, it's added because what I wanted to show is basically that even with a very highly informed pruning technique, it has, like, pruning has its own issues, right? Sparsity has a representational issue. That is what is getting highlighted here. But everything else is basically moderately informed pruning techniques, which are better, like which are anyway less. So what it points out is if you can do informed parameter sharing or informed projections, you might get something better. But that, in my experience, has other issues. Yes.
So this shows the time you mentioned it, like have you done the bigger, like full imaginative response? Like, will that work for that?
Yeah, it will work for that as well. I have some experiments. They were not put in the paper though. Yes.
What is the small model here?
So small model is just basically you take this ResNet and then when you like basically reduce the number of hidden neurons
And
to get the parameter memory.
You made it compatible with your model?
We made it compatible in the sense that they have the same parameter memory. Yeah. Yes. You have question? Oh, push. Okay. So we find that this observation of comparing against different efficiency techniques is consistent across domains. So we tried graph domain with some attention networks. We tried some word transformer based stuff. We tried this vision models with convolution models. And then,
see the transform, can you go back?
Yeah.
So what is?
So this is done back in 2021, where I was just trying to train BERT, and we didn't have the resources to train entire BERT. So we trained BERT-like model on like polarity tasks and saw like what kind of compression we see. The point was to compare, again, that paper was more about comparing sparsity versus sketching. And so pruning versus stable RPS. Yeah.
But these curves are different than other curves. So what?
It has very less data points. I think if you do like a very exhaustive, like this, these are,
just a couple
yeah.
of points. Good, thank you. And you don't have other comparison because there you have 3, 4. Here you have 2, green and blue. And
yeah. So again, this was actually done in a different paper. So that time we were just showing these results, but it kind of makes sense in this context as well. So I wanted to put it here. Yeah. So most these results are from the same paper, so you will see the same kind of setup here. Yeah. So in fact, if you look at the recommendation, right, the curve that you see is actually very flat. You can go to very high compression and still get a very good quality model.
So what's the problem recommendation? What does that say?
So this is, I think, Keto Kaggle with, Keto Kaggle dataset for different models. Yeah. But again, because we see such good results in recommendation, I want to show you what can be achieved with stable RPS when you try to apply it to an industry benchmark, right? So I'm going to talk about DLRM MLPerf benchmark. So DLRM is a model that was open sourced by Facebook, right? Why this is interesting is because it's widely adopted in industry, or some variation of it is being used. It's a very peculiar kind of model. We'll get to that. But even at Facebook, it is like apparently said that 70% of AI cycles are recommendation, right? So a lot of these industry folks are heavily using these kind of models. So if we can reduce the parameter memory of these models by a large factor, we can show some real improvements, which are applicable directly to industry. So let's try to apply elastic parameter memory, specifically the method stable RPS, to the industrial scale model and see what happens. So this model is peculiar, as I said. So it has two kinds of components. One is the MLP components, which have a very small memory footprint, and the embedding table component, which has the most of the parameters. And in fact, the dataset that we'll be talking about is a 100 gigabyte size model, but the MLP sizes are just 10 megabytes, and the embedding table has 100 gigabyte of parameter memory. So what I'm going to do is I'm going to replace the embedding tables by elastic memory, what we have developed, right? And I'm going to see what can be achieved, how small a memory footprint can you get. So if I do that, we find something phenomenal. So you can go from 100 gigabyte model to a 10 megabyte model. So in terms of embedding tables, so 20 megabyte model, and you can still achieve the same quality of the model. And this kind of compression you couldn't have seen if you were trying methods like sparsity or quantization or any of the existing methods that you think about. And indeed, we get this green line that we were looking for, not universally across different domains, but at least in the domain of recommendation.
So this is the same method that hashing.
Yeah, the same setup applied to recommendation, actual bigger model.
Why is so superior in recommendation compared to the other?
Can you repeat the question? Sorry.
Why this model is so superior in recommendations compared to the other?
Yeah. So there are a couple of reasons, I think. So one reason is, first of all, this is the model that is sized 100 gigabytes. So it's a very big model. Generally, large models tend to show a lot of power law. I mean, there's a lot of sparsity. Sparsity in the sense that important sparsity, right?
But the sparse models do not achieve.
Yeah, the sparse models will not. So in this case, it's even like very peculiar in the sense that the main thing is embedding tables, right? So it's an n cross d matrix, right? N is the dimension that is exploding. D is generally 128 or something. Now, if you start sparsifying this model, right? Once you sparsify beyond b times, you start getting the zero embeddings.
What for the low rank base?
Low rank based, like even if you low rank decompose it, you still have to have the n, right? How do you get rid of the n? So people do something called tensor decomposition in this case, where they basically convert this embedding into a tensor and then they decompose it. So that essentially, if you think about it, if you do that tensor decomposition and you have a random mapping, it's essentially parameter sharing. It's essentially this happening in the background. Okay, so if you're able to reduce the memory footprint by a large factor, you should see some improvements in inference and training metrics as well, right? So let's see what happens in inference. First of all, we are able to deploy this model on a single GPU now. It has a very small memory footprint, right? So we are anyway reducing our resources by a factor of 8. And then the latency of this model, we can improve it because it has, again, a very small memory footprint, plus the fact that it does not have any communication costs. So that can be improved by a factor of 3. So overall, if you think about the inference cost, that goes down by a factor of 24. And if you use 24x less resources, you're going to have 24x improvement in all these different metrics.
But that is not really quantified, right? I mean, these are complex systems, so you may reduce the resource requirement, but it may not translate to 24.
Yeah, that is true. This is back of the envelope calculation. This is trying to show you what is achievable.
The previous slide,
Yeah.
the bracket you are putting, these are, how do you find the y and x values?
So this is actually coming from y and x values in the sense.
Did you do an experiment for these values, or are you
Yeah.
showing the efficiency?
Yeah, because this is a DLM MLPerf benchmark, which has a, basically they want to get a quality of a model, like a specific quality of a model. That's how long you train the model. So in that case, you have the AUC that you want to achieve. And what we're trying to see is whether we can achieve that AUC with smaller footprints. So that line is determined. And that is what you get if you train a big model for one epoch, after which anyway it kind of degrades. So big models have a problem, like if you know about recommendation, they can only be trained for one epoch. Once you start training for more than one epoch, like it starts overfitting. So the best accuracy you get is the accuracy that we want to reach. And we are able to reach that with this one. In fact, we are able to beat that. But that's not the point. Yeah.
My point is that things are not so linear and so on, right? So if you plot it like this, if you really compute and plot it, the stars will not be that. There will be some randomness, there will be complex systems, so it will be different.
So what do you mean? You want to basically give a star for the exact value?
Yes.
Yeah, the thing is, like, you can do that. The question is, when do you stop training? Because with big model, it's very clear. But with small models, I can keep, like this model, 10 megabyte model, I can just keep training. It will get improving. I don't know when to stop. It basically, like, this is 0.8025. That's the limit that they have given. Like I trained it till 0.832, like 8032. And it was still training. It was still running. There was no overfitting. So it's just like, I mean, yeah, if you want to get the exact number, I'll tell you like these numbers are like these, all the yellow things are a little bit higher than this. Because they can be trained for longer times. So in fact, we get like better results. But the easiest way to like show this to people is that we beat the result of original model. Okay, so what happens with training? So again, we can train this single model on a single GPU. So we reduce the resources by a factor of 8. We're able to get a training time iteration improvement by a factor of 4.36. But the flip side is because you have less number of parameters, now the convergence becomes slower. So you have to train these models longer. But you can see that most of this latency improvement almost compensates for the slower conversions. So again, overall, you have a good enough improvement in all the different metrics. So this is like applying the elastic memory that we created to a real industrial scale model. Okay, so we are at 10:45. Is 11 o'clock a hard limit?
Yeah, I think so, because they're
Yes,
all
because
things
meeting at-
scheduled for you, right? You have meetings.
Okay, so let's hold on to the questions till the end so that I can just get through it. Okay, so I'm going to switch gears a little bit. I'm going to talk about some of the immediate problems in AI related to efficiency. So I think the biggest problem today is that you have these huge models that are open sourced and you want to deploy them, but you don't have enough resources. So specifically in this section, I'm going to briefly talk about how to deploy LLM in limited memory, right? So let's, before going into that, let me try to quickly give you what the memory bottleneck is. So let's talk about KV caching. So, LLMs are these autoregressive decoders, right? They decode one token at a time. And while doing this decoding, it has to compute all these decoder layers. I mean, each of the layers will perform some kind of attention. So the attention looks like this, the softmax equation that you can see. The thing is, in each of these layers, the Q embedding from the last token will essentially access all the K embeddings, perform inner products, get attention scores, and then those scores are used to sum up these V embeddings from the previous tokens to get into the final embedding that we want. Okay. Now, the thing is, because these K and V embeddings are going to be used for each subsequent token generation, it's a good idea to just store them as and when they're created, so that you don't do the recomputation. But the problem is that this is called as KV caching. And the problem is that KV caching becomes a memory bottleneck. To give you an example, if you were trying to run a 175 billion parameter model, the model size itself would be 300 gigs around. And if you were to run this model with a batch size of 128 and sequence length of 2000, then the KV cache footprint would be 950 gigabytes. So running these models is actually quite hard in limited resources. So we want to ask the question if there's a way that we can reduce the memory footprint of KV caching. In order to solve these kind of problems, when we are given a model and there's no scope for fine-tuning or changing the model, generally what you want to do is you want to look at the properties of the model that you can leverage, right? So in this case, the problem is attention, that you have to attend to all these different embeddings. But the question I want to ask is, do you really need to attend to all the embeddings? And the answer is no. And you can think about it in terms of softmax as well, right? Softmax is essentially just argmax, a software version of argmax. So it should be able to get the close enough approximation to the embedding by attending to only a few tokens. That's what we are seeing in the figure on the left, which is showing you the attention maps. So in this case, I'm showing you attention maps for different positions, right? On the x-axis, I have sequence position. On the y-axis, I have different attention heads. And these are attention scores which are binarized. So dark green basically means that the contribution was significant, and light green means it's not significant. So you can see that there is presence of sparsity, which is not really surprising because we are using softmax. That's the first observation, but that doesn't solve our problem because we need to still be able to predict this sparsity, right, in order to use it for subsequent tokens. So that is where the second hypothesis comes into the picture, which is persistence of non-importance. The hypothesis is such that if there's a past token which has not been useful in recent generations, then it will not be useful in future as well. That's the hypothesis. And basically, if you look at the attention map at different positions, you see that it's more or less true. Things which are light green here are also light green here, are also light green here. It may not completely be true, but it's more or less true. And that's what enables us to get a good approximation.
So what do you mean by generation? Recent generation.
So what I'll do is, in effect, is at this point, I look at, let's say, a window here, look at what all contributed to that window, and then things which are on the lower end of contributions, I'll basically drop them.
You mean the previous up to that time?
Yeah.
Up to that token.
Yeah, that's what we want to maintain.
Yeah.
Is that whatever is in this window, let's say this point, I basically sparsify based on how they have contributed differently, and I keep that sparsified.
Generation may not be a good word.
So generation of tokens, because it's like autoregressive generation. But yeah, maybe I'll fix that. Okay.
So it's like, there's this causal attention, like people, we do these kind of things in the standard sheet.
So what kind of?
See, the one is we see the full attention for all tokens, paid attention to all, and the other one, for others, called other attention. You look at up to what you observe, only use those for attention.
Like recent windows. Yeah, but I think in the limited things that I know about attention, because there's so much out there, I think like even still these systems are probably more powerful. They show better results on causal attention. Yeah. So anyway, so if you do that, then you can see that with a 5x reduction in KV cache memory footprints, you can still maintain the quality for most tasks. And you can further combine it with quantization or existing efficiency techniques to improve it further. So you can get like 20x compression with minimal loss of accuracy. Okay, so I'm going to talk a little bit about my future directions. So what next? There are three main directions that I'm excited about. The first is what I like to call as fuzzy core AI. And the idea follows from the elastic memory that we were discussing. So that is like one piece of this fuzzy core AI direction. So what we want to do is we want to build an AI system which is built from probabilistic computational code. So we already saw elastic memory, but let me give you some idea of why I think this is a good idea, right? So this is how the LLM model looks like, right? We saw it just in the previous slide. Now, there are two main kinds of computation happening here. So one is the attention computation, and the other is the MLP computation for transformation, right? If you think about attention, we know that attention is sparse. right? In fact, it is somehow performing this top K retrieval, right? Based on inner products. So essentially it is solving the maximum inner product search problem, but it's doing it exhaustively at this point. And if you look at the feed-forward network, the activation is the one that imposes the sparsity, right? Which gives you the nonlinearity and the capacity and everything to MLPs. Because we fix the sparsity, then essentially this is just a linear transformation. So you can think about activation, especially ReLU activation, as positive inner product search, if you may. And essentially these techniques, like these two problems, are very the IR community, the information retrieval community, is very familiar with these problems, and they try to find accurate approximations for these problems. And they have generated a lot of probabilistic methods to solve these kind of problems. So even the existing model that is giving you such great accuracies is performing some kind of retrieval inside the model. Maybe it is doing it exhaustively, but we can replace it with some sort of probabilistic or IR kind of techniques. What we want to do in this project is we want to put the information retrieval probabilistic methods into the core of AI, making it the first class citizen of AI model building. So that's the overview of what we hope to achieve in this direction. So we want to research on probabilistic components. It will span different areas of research, like it will be it will have some system component, it will have machine learning, it will have some theory about how to analyze these components and so on. And we hope to get artifacts such as we want to get open source package, which can be plug and play inside PyTorch. And if we get enough compute in the future, we would want to train these models as well to publish. The next.
So can you talk about
Yes.
What's the whole idea?
Oh, so the idea is basically that, so right now we are doing this, so everything is based on linear transformations, right? But even then, if you look at the current computation, like what it happens is, this is a sparse computation in some sense. This is also some sort of sparse computation. If you can add sparsity in a way, then you're able to do this with, you can give this enough capacity. So even though this is happening, right now it's happening exhaustively. The attention computation is exhaustive, it computes everything. But maybe if we can just incorporate the approximate ideas that are developed to solve these kind of problems as a first class citizen. So it has to be present inside while training the model, right? Like we have to take a probabilistic view on it, in the sense that the way we did it with elastic memory, right? We added projections, but then we also trained accordingly. So if you do that, then my hope is that we will be able to achieve much better quality resource trade-offs. Yeah. The second direction is what I like to call as flex deploy. We want to create a flexible approach to model deployment, given the amount of resources that you have available. Again, if you know that, current state is such that you have you have a fleet of models, which takes some resources, gives you some accuracy, right? But in most cases, the resource availability is not aligned with these models, right? So you might have something which is intermediate. And this resource availability can actually be dynamic as well, right? So at some points, systems might be overloaded, you have very less resources. At some points, you have the full width. So the question is, how do you use your resources the best way possible? So can you create a model which lies somewhere between? That's the problem we're going to look at here. In fact, we know that we have some access to existing efficiency techniques, plus we can make some observations about how model is executed, the way we saw in KV cache sparsification. So maybe we can even get better than a simple interpolation between these two qualities. And if you're able to nail this down completely, then we might just have a better deployment scheme, right, for models given the resources. So that's essentially the problem that we'll be solving in flexible deployment, trying to get the best out of the resources we have and try to look at all the different efficiency techniques. So in terms of research, we will be trying to look at different execution techniques, trying to leverage model characteristics. We'll also be looking at different combination of different efficiency techniques. There's no holistic framework, as far as I know, about how to combine sparsity with quantization, with maybe this kind of attention sparsity and so on. So again, it will span some areas, and we want to make open source. We want to make things as open source as possible. Put out projects that people can directly use. And the third direction that I'm kind of building right now is what I like to call as the omniscient AI, Omni AI. So the idea here is the existing models have a lot of issues. So we want to look at how can we generate the next generation model, which preferably has access to unbounded knowledge. So it should be able to work with unbounded external knowledge, and it should solve current limitations of the problem. So let me tell you some examples of what the current limitations look like. So this is how machine learning looked like back in maybe 2016 or 15, right? When models were small, most of the data lied outside the model, right? And we were the ones deciding, okay, what data should be processed by what model and so on, right? But things have changed significantly. The data has been pushed inside the model now. It has most of the data. And essentially the input that it requires to function is very small, right? As compared to the data that is essentially recorded inside the model. Now this has a lot of problems, right? First of all, if there's data inside the model, these models go out of date pretty fast. So they need to be retrained on the new data. We cannot modify the data easily inside the model.
What do you mean by that? I mean, we have used bigger model, but we have used the data, right? You say data is inside the model because data has been used.
Yes. So not just used, it's also stored. It's also like recorded, right? There's a lot of factual information that lies inside the model directly. So this model is not only having the reasoning capability, it also has some data that it needs for reasoning capability, but it also has a lot of factual data.
That's not a model.
But that is how LLMs are today, right? Oh, if you say
like if you ask who's the president of the United States, it is memorized inside.
Yeah, but it's in the model, right? So you cannot say, well, these things in the model, the attention, all this thing is the data.
Not the computation, but the weights. They have the data.
Yeah. Weights has the data. That's true. But I think it's not really correct to say, because every model is trained on data. It has data. So you can just say we are increasing the data in order to train a bigger model. We need large data, and that's it. I don't think.
Okay, so this is what I'm saying.
The training process is transforming the data into a way that makes it efficient.
Yeah, model has become data remains the same. Whatever data we use, it's
yeah, that is true. But think about it this way. Yeah. So maybe you had a small model previously, and it was let's say a small language model. But if you ask exactly who is the president of the United States, it needed access to external data to be able to answer that, right?
No, that's a different thing.
Yeah,
right?
That's true. But I'm trying to just say what I'm trying to say here.
Yeah.
So that's the difference I'm talking about, where the data or the information is a lot of information is stored inside the model.
But the reason these systems are impressive today is because they know so much.
Yeah, there's no so much.
So
it's a very big model, and model size is stored all the weights. You forget about data, right? You cannot go to the model and say, well, give me that element. It doesn't have that. So
it doesn't have that in that same format, but it does have that in some format.
You cannot recover that.
You can still recover facts, right?
We stand from complexity. But I think it's overstated from my point of view. But you can continue.
Yeah, but I mean, I think the framework that you can use for understanding what I'm trying to say is exactly this. Think about factual equations, right? The president of the United States is, and it knows the answer, right? That's the kind of factual information. Let's try to stick to that for trying to understand what I'm trying to say here. Yeah. So, and okay, I want to comment upon one statement of yours, but I'll come to that later.
Sure.
Yeah. So anyway, the problem is that data modification is not possible. You cannot easily modify data because it's in the model. And then there are problems such as hallucinations, which, I mean, there might be a lot of reasons for that, but partly it's also because you don't know what data is being used to generate the answers that it needs, right? Apart from that, there's one big problem that people are trying to look at, which is the quadratic blow up in external. Basically, quadratic blow up when you try to ingest a lot of input or a lot of external data. So the idea in this project is basically, first of all, to resolve the computation challenge, which is you want to create efficient sublinear mechanisms to retrieve information from outside. And then you want to train the model holistically, in the sense that retrieval is part of the training process. And the hope is that the models are not, I mean, I know that models are powerful because they have a lot of data, a lot of information, but maybe there's a balance, right? Maybe the model does not need to know that the president of the United States is so and so to be able to perform everything. So maybe there's a part of data that goes into the model that can lie outside. So as long as we give it the efficient access to this data, it should be fine. That's the full idea. And you want to investigate the balance. There's no hypothesis. The hypothesis is that you don't need all that data inside the model. And then
retrieval augmented.
Yeah, that's kind of thing.
So retrieval augmented is So RAG is one ad hoc way of doing that, right? It has its own limitations, right? So what I want to do is like train a model which has RAG is like it has to subsume RAG. RAG has to be a part of its technology, like not something that you add on the top, which is what people are trying to do right now. Okay, and then once you have the system, maybe you can just expand the amount of data because now you have access which is very efficient. So if your model has more data, it can be more powerful. The potential benefits of this is, first of all, you probably can get smaller models. I mean, if you think about it, like even though we say that models are it's useful to have all this data inside the model, think about every token generation, right? The next token generation needs you to bring the entire 100 gigabytes of model inside the GPU, like shared memory. Do you think it needs to bring in the whole 100 gigabytes of parameters just to get that next token there? So that's the kind of efficiency issues that you see.
Right, so the reason that I'm using big model is good. It does what you want. So yes, I mean,
yeah, so that's what we want to investigate. Is that something that is fundamentally has to be there? Is that a fundamental limitation? Or is that something that is artifact of the way we are training these models, right? We don't know that yet. So that's exactly the kind of system that we want to investigate. And maybe we can find something better there. So we can have smaller models. We can have model capabilities via external data. So this is something that I think is quite interesting and exciting, is that the capacity of the model, the capability of the model depends on what data it has access to, which is very different from what you see today. If you want better models, you have to build larger models and then they do what you want to do. But maybe that's not the right way to go about it. We can partially at least solve these kind of issues as well, like privacy, right? If your model doesn't have access to private data, it's anyway good, right? It will not act upon. Then hallucination, because we can probably build systems as to see what kind of data did it access, try to create the citation, the way we write research papers, right? Everything is cited by, okay, this comes from this and this and this location. So we can build this kind of system. And of course, we can update the data as well, as and when we want, because it's a separate independent object. So that is the overview of Unsigned AI. I think we're already running out of time. So yeah, essentially that.
You have a shiny slide. You know, better tell me how to put the facts.
Yeah, for sure. This is something I figured out recently because I was like looking at watches, very distracted. Thank you.
Okay, so I guess whomever has questions should try to catch him at various points in during the day. Okay, thank you.
Yep, no problem. Very good. Yeah.
There are no questions in the chat as well, right?